Capito? Certo, non abbiamo riferimenti. Allora, siamo rimasti con Cecilia siamo rimasti d'accordo che lei sentiva prima il preside, poi in questo tempo, in queste 2 ore prossime, e poi mi avrebbe mandato un WhatsApp e poi lo chiamavo anch'io. Capito? E tu intanto, e poi facciamo il punto, sì. Ciao, grazie, ciao ciao. Good afternoon, everybody. Okay, so we are ready for starting our lecture, and I want to share my presentation here. Seconds. And what I remind to do today is the following. I would like to complete the introduction of our elementary model, and next go ahead with the general theory and develop keeping on developing the theory, or the general theory of for unsteady flow. So I want also to introduce my second exercise, and therefore now let's go with the recording the lesson, and okay, and here we have our whiteboard, okay, and okay. First of all, I would like to have an announcement. This announcement is concerning the very early decision on the government decision on the university lecture, and the last disposition of this government dispatch is on the lecture for the academic years after the very first academic year. In particular, this kind of course, like the aeroelasticity course, which are courses in the second or in the third year, for example, are to be taught only from today on in remote remote modality, and therefore I'm very sorry, but from today on we will have our lecture only in remote condition, okay, on distance. And this is because of the last government decision. And different is the case for just enrolled student in the first year, and also, but this is an interpretation to be verified, also in the first year in the master degree. In the master degree, we all are not unsure of this item, but we are going to verify this point. Okay. Go back to our question on this on our model. I am alone in my room here, and therefore I am free to use or not my mask. However, I have my mask in this way, just to be an intermediate position with you. However, I want to conclude this model, and I want to go ahead in the general theory today. So this model is the model of typical section. We're going to use this model, and I emphasized the point that the equation of this model are just identical to the equation of a finite element model for an aircraft or a wing. The only difference is on the representation of the unknown, in the sense that here we have rigid body motion, a vertical rigid body motion, and a rigid rotation, and we have as equivalent shape function this function here. We don't know, we don't have this function. Yes, we have the psi and psi function like this, equal to 1 for the first degree of freedom here. And we have the other function, psi2, equal to a triangle shape function, just representing the rigid body motion as psi2 here. Psi2 function here is just the x function. And therefore, we are currently representing the rigid body rotation in a linearized form, okay? After this, we have also emphasized that this point of view is quite identical to a finite element discretization of a model. And we obtain two matrices, the mass matrix and the stiffness matrix, which are currently symmetric and positive. And we have also a forcing term. And of course, this forcing term is composed by the two Lagrangian generalized force EH and E alpha, and these are currently representing the projection of our physical field on the shape function. Okay, and in the first case for EH, we obtained directly the lift, and in the second case for E alpha, we obtain the aerodynamic moment with respect to the center O of our triangle shape function. What I said is the following: that we have considered this translation, the translation of one fourth of the chord, and therefore this shape function representing the rotation with respect to this point here is a rotation with respect to 1/4 of the chord point, okay? And so, correspondingly, the moment evaluated by projecting the physical shape, the physical force onto this shape function is representing the aerodynamic moment with respect to such point, with respect to 1/4 chord, which is the region of our reference axis. Okay, so we have defined and clarified the role of this variable. The next step We have also commented the role of the corresponding mode and frequency for this model. The frequency obtained by imposing the determinant equal to 0 are not, absolutely not, the quantity we obtain taking this square root of kh by m or kh alpha by jg, in the sense that these here are the natural frequency of the uncoupled, absolutely mechanically uncoupled system, which we have when the center of mass is superimposed with the elastic standard and is superimposed with the point O, or the point of we use for representing the dynamic. In that case, the vertical motion is decoupled with the rotational motion, in the sense that in this case, which is clarified here, in this case, when we have this uncoupling condition, if you impose an initial condition translation and release, you have just a motion with the L-fold going up and down. If you impose a rotation as initial condition and release, you have only rotation as a permanent harmonic motion for this unforced initial problem, okay? But in general, we have not this condition. In general, this point here, the mass center, is a point which is distinct with this other point here. Excuse me, I want to write to be clear with you. Okay, so this point here is distinct by this point here, the elastic center, which is distinct by this point here, which is currently representing the vertical displacement. Okay, but in the case we have a unique point, the structural dynamic will be uncoupled. And in that case, the natural frequency, the first natural frequency is omega h, and the second natural frequency will be omega alpha. Okay, I want to conclude my discussion by introducing our undimensional quantity. And the undimensional quantities are introduced considering the first equation, for example. Write the first equation and then we want to undimensionalize this equation. The first equation is the following. We have m h dot dot plus mg, yes, m by xg alpha dot dot plus k alpha h plus xe k alpha h alpha equal to minus lambda. I have written just the first equation here. I have written this equation developing this matrix product and including this. Okay, and if we divide by all the equation, the left hand side and the right hand side, this minus L is EH, okay? If we divide by this quantity, and the quantity is a quantity representing a force per unit length, mb by omega h alpha, we have and note another point. For steady aerodynamic, we have that alpha, the lift force per unit length for a dipole dust. We have the dynamic pressure 1/2 rho by u infinite to the power 2 multiplied by a reference surface, and the phrase that we have an airfoil like this, we have a thin airfoil, very thin in this x direction, and we have in the y direction we have 1, because we have a one-dimensional. Okay, we are considering a 2D aerodynamic. Okay, so the reference surface in 2D, we have a chord here. The chord is equal to 2 times the half chord, excuse me, this point. But for this reason, we have 1/2 rho u infinite to the power 2 by 2b by 1. Okay, and what about this is the reference surface, and here we should have the lift coefficient, and the lift coefficient is something like CL alpha by alpha. Okay, so in the steady aerodynamic, you have a first signal of the fact that the forcing term is not a forcing term at all, because this L is depending on alpha. But this is steady aerodynamic. Pay attention, please. It's unsteady. Okay? And in steady aerodynamics, so you have this, and therefore this L at the end of the story for steady aerodynamic, I want to underline this, is something like minus 1/2 rho u infinite to the power 2 by 2b, and CL is, remember, CL is 2 pi, okay? Because the lift coefficient is 2 pi in the ideal case, CL alpha by alpha, and that's the dependency on alpha of the right-hand side. So if you use the steady aerodynamic, the stiffness is actually behaving like a stiffness. The lift is behaving like a stiffness because you have a coefficient by alpha. Just right here, you have this coefficient related to the spring by alpha. Okay, but this is not exactly this is not actually the case for the unsteady case. Probably we should have some more complicated because of the wake mechanism, blah blah blah. We studied in general. Okay, so going back to the undimensional equation, we want to divide also the lift by mb omega alpha in both sides, and therefore we have the following. We have h. Excuse me. We have h. Okay. M h dot dot by mb omega square alpha plus m x e elastic center alpha dot dot divided by m b omega alpha square omega alpha square plus I want to start this contribution, and we have k h h by m, the same quantity. And
professore,
finally,
ci si è passato il video e io anche non vedo più lei che si muove sulla videocamera né lei che scrive sulla lavagna.
Ok.
È molto disturbato. Molto disturbato nel mio caso. Non so.
I am connected with the faculty network and web. I don't know. Can you hear me and can you see me? Can you see the video like this?
Allora io ma non vedo né lo schermo né il video.
Okay, I can go out and go inside again to the meeting. So wait for me, please, just a second. Much better?
Decisamente.
Can you hear
Ora
me?
sì, prof.
Okay. 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 I have the message about the web, which is very weak, very weak. I have this message on my. However, I am in the faculty, so I don't know. I don't know. Okay. Can I'm trying to share my screen again. Okay. What about now?
La sentiamo bene, ma non si vede, tutto bloccato.
Okay. The video, can you see my screen?
No, io non la vedo.
Can you?
Io lo vedo blu.
Come è rimasto su Windows Default.
Okay. Okay. I try to use the other connection. The other connection. Let me. I'm sorry for this, but. Okay, now I am using another network, and can you hear me? Can you see me in the screen? Hello?
Io come prima.
Guarda, io non vedo lo schermo, la sento male.
Sì,
Professore, mi
però
perdoni.
c'è gente che dice
Adesso
che...
funziona. Adesso funziona.
Però ragazzi, controllate anche la vostra di connessione, perché io c'è gente, stranieri soprattutto, che mi dicono che mi vedono molto bene. Quindi non lo so fino a che punto può dipendere da me, eh? Quindi io non lo so, andrei avanti, se per voi va bene, però se non vedete la... D'accordo? Ok? If you don't see cat whiteboard, please, and I'd like to go ahead. Okay? And so I have here my whiteboard. Okay. And this is my first question. And first equation of motion is actually analyzed. This equation of motion is indicating a force balance per unit length. So I divided the left-hand side and the right-hand side by this reference force here. This is a reference force represented by the multiplication of the mass per unit length, the F-span length, and this strain natural frequency, which is the natural
Scusi,
frequency.
prof, io non vedo la lavagna, non so se sono solo io o di
No,
nuovo.
neanche io.
Quanti sono che non vedono la lavagna? Per favore, allora ditemi chi non vede la lavagna, mi scrive non vedo la lavagna. Per favore, chi non vede la lavagna scrive non vedo la lavagna. Ok, va bene, allora non possiamo fare lezione oggi, mi dispiace, io non so cosa fare, adesso proverò a rispegnere completamente il computer e avviarlo. Mi datemi un minuto, se sarà ancora così, la lezione è sospesa. Grazie. Mi potete vedere adesso? Can you see me now? Ok.
Adesso molto bene.
Ok. Ok. So. Okay. Okay. We are here. Okay, so you can see my whiteboard now? Can you see the whiteboard now?
Sì, ora sì.
Okay, thank you. Please collaborate, please. Okay. And now we are trying to undimensionalize this equation, and so we have this, and after this operation, and we have minus L divided by MB omega alpha square, and we have this, and I want to do a comment to you. We have I want to introduce an undimensional time. This is very important in elasticity. We have the possibility to introduce a time like tau, undimensional time, which is equal to the dimensional time divided by b, the half length, which is a length, and multiplied by a velocity. Okay, so this is undimensional time. And together with the time, we have also related an undimensional frequency. This is the dimensional frequency, omega, time, and frequency, which is not the natural frequency, which is the frequency in the Fourier domain, okay? And this frequency has a similar, or better, a reciprocate definition for the undimensional frequency, and here we have B by U infinite to define our undimensional frequency, also known as reduced frequency, or Strual number, HAL number. So if we introduce this time frequency undimensional quantity, when you take a regular derivative with respect to the physical time, this is equal to a derivative with respect to the undimensional time, but t is equal to tau b by u infinite. So we have b and we have u infinite. So anytime you want to derive physically a quantity, this derivative is equal to the derivative with respect to undimensional time by u infinite by b. And this undimensional time derivative is indicated with, I want to indicate that the dimensional derivative with the prime, with a dot, so indicating the derivative of f with respect to the time, and the undimensional derivative with a prime, which is the derivative of f with respect to tau. And therefore you have that f dot is equal to u infinite by b by f prime. Okay? So here we can to go back here and write the following. We have that this quantity is equal to h prime prime by b by u infinite 2 times. So it means that you have to multiply this factor 2 times. So you have u infinite by b square. And you have also this b and this omega square alpha. However, we want to introduce also undimensional quantity, like an undimensional h. So we want to introduce an undimensional h bar is equal to h by b. This is this vertical displacement, and therefore here we have the quantity I have indicated, and next we have this simplification, and we have an undimensional x quantity like c e equal to the dimensional 1 by b, and therefore we have an I'm sorry, this is a mistake here. This is xg, center of gravity. Look, we have center of gravity here. And so we have xg by b, and we have this second time derivative, which is an alpha prime prime, but multiplied by u infinite by b square, and we have also this omega alpha square, and here we have kh on m, which is omega h square. So another definition on dimensional quantity. We have, this is non-dimensional, this is the definition of h alpha and omega h, which are the power 2 equal to k on m and k alpha by j alpha. And so we have omega square by omega alpha square, and we have this ratio, which is h by alpha, h by b. The final term here is again plus an xe by b, which is undimensional, like this. So we have an undimensional coordinate of the center of mass, xg, and again kh on m is omega square h divided by omega alpha square, and this is equal to our undimensional lift, mb omega alpha square. So at the end of this we have this quantity, but note this here is cg, this here is the ratio, the square of the ratio between these two frequencies. So we have another undimensional parameter, This is very important in elasticity. This parameter is the ratio between the omega h on omega alpha. Well, what is representing this parameter? Omega alpha is not the first natural frequency, and omega alpha is not the second natural frequency, but they are the first and the second natural frequency in the case of uncoupled structural dynamic system. However, the first of these two, although in the uncoupled case, is representing something like related to the bending, and the other one to the torsion. Therefore, this ratio is something similar to the ratio between the first bending natural frequency and the second torsion natural frequency. For an aircraft, we have that the first bending uncoupled is something like 2 pi, the first bending frequency in Hertz. And this number for a civil aircraft is something like 5-7 Hertz. And the second one is the torsional natural frequency. For a civil aircraft, the second is about 10 F alpha, is something like 10-15 Hertz torsion. Therefore, typically, this quantity is a quantity less than 1. And in the case you want this quantity be close to 1, you have the first bending and the first torsion. When I say first, in this case, I have in mind the case of an actual aircraft with more frequency, because we have a continuous discretized system. You don't have 2 degrees of freedom system, okay? But in this case, we have in mind the interesting point that your bending frequency is close to the torsion frequency. In the case, capital omega is close to 1. But typically, capital omega, in the practical case, is a number less than 1, okay? Okay, so we have omega here, and note that this is the undimensional h 2 prime, and this is the again the undimensional h, and here we have the square of omega to the power 2, excuse me, capital omega to the power 2 to the power 2, and here I forgot alpha, but we have a state space variable alpha, okay? And the very last quantity to be introduced to complete our scenarios is the undimensional flight speed, just like u hat. And this u hat is the flight speed u by omega alpha b. Okay? And after this definition, the first equation becomes the following. We have u hat to the power 2 h bar prime prime plus cg u to the power 2 alpha 2 alpha prime prime, excuse me, second derivative in the animation with respect to undimensional time, plus omega square, capital omega square, h bar, plus ce omega square alpha equal to, and we have minus lift divided by m omega alpha square b. Okay? And remember that this here at the state space variable, the n-dimensional state space variable with related derivative, and here the other are the n-dimensional parameter. Okay, you can do the same work for the second equation. Do for exercise, please. And in the second equation, we have a similar n-dimensional equation. And just a note about this u hat to the power 2. We have this u hat to the power 2 here, because here we have, excuse me, here we have this, and we have this, and these two are u hat to the power 2. Okay? So this is the final n-dimensional equation, first equation, and the second equation, following the same procedure, we have this equation. We have Cg u hat to the power 2 h bar prime prime plus we have a term of this type, r alpha to the power 2 plus 2 times Cg by Ce minus Ce to the power 2 by u hat infinite alpha prime prime, and finally we have plus omega square Ce h bar plus r alpha square plus omega square Ce to the power 2 by alpha equal to 0 or equal to the moment with respect to the origin. And again, this second equation, we have the state space variable here, 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 and here. And with these two equations, you can see clearly, the mass, the mass contribution this is mass matrix, the new n-dimensional mass matrix applied to h bar prime prime alpha prime prime. And here you have the stiffness contribution in the new n-dimensional variable, this here, represented by the n-dimensional stiffness matrix as applied to the n-dimensional h and alpha. Okay, the very last dimensional quantity is this R alpha, and this R alpha can be introduced as in the following. If you consider you have Jg, which is the principal moment of inertia, and we have also the J alpha, which is the moment of inertia with respect to the elastic center. With respect to the elastic center. This moment of inertia, J alpha, can be written as the product of the mass by a gyration radius. In Italian, raggio di girazione, in English, gyration radius, which is the square quantity, the square of the length. This is the length. This is the radius of gyration with respect to the center. Okay? And if you introduce in this way this rho, you also introduce R alpha as the animation radius, like rho alpha divided by B. Okay, so this is the radius of gyration, the animational radius of gyration that you have here, for example, here and here. You may have a very good exercise of solid mechanics by undimensionalizing this second equation here. Just to recap our undimensional group, we have this undimensional quantity. The undimensional variable is this, and the undimensional parameter are this dimensional elastic center location, the dimensional radius, the dimensional center of gravity location, this undimensional speed, light speed, and we have this undimensional radius of duration with respect to the elastic center, and the undimensional frequency ratio. Okay. Another interesting quantity we have here is the mass ratio. You can't see the mass ratio at the moment, but you can realize the presence of a mass ratio, in particular the ratio between the structural mass and fluid mass, so mass ratio. If you consider, for example, let me specialize this here. Where is it? Okay. Consider static aerodynamic. In the case of static aerodynamic, you have the following. You have lift divided by the n-dimensional quantity, which is mb omega square alpha, and here we have mb mb omega square alpha. Okay, but L is 1/2 of rho u infinite square by 2b by 2 pi by alpha, and note that we have a mass ratio because here we have the air density and structural mass per unit length. So you have a potential mass ratio, okay? And if you simplify this ratio in this case, simplify this 2 by this 2, you have here something like pi, excuse me, something like rho pi B square by M. And we have U infinite square B square omega square alpha. And here we have also a 2 by alpha. Okay, so we have two groups. Look, for representing this ratio, we are representing the ratio between undimensional force, this undimensional group, and this is recognized to be hot to the group. So we have a new group. The ratio between rho by B square by M. To call this group like A. And this is a mass ratio in the sense that we do. In fact, look, representing this, we have A defined like M pi rho B square. You have an iPhone profile, very thin, and the length of this wing is unitary because we are considering two-dimensional flow, and this length here is 2b. Okay, so consider a cylinder of air having this 2b as diameter, like that. Consider this cylinder of air. You have a mass of air including this cylinder. And what about the mass of this air? The mass of this air is equal to the density, the volume density, multiplied by the volume of the cylinder. And the volume of the cylinder is the base of the cylinder, which is pi by b to the power 2. This of cylinder, which is unitary. Okay. This is the volume of the cylinder, and the volume by the density is equal to the fluid mass in the cylinder. And so the density ratio is representing the structural mode for unit length by the fluid per unit length. And this number is important because this number is of the order of magnitude of for an aircraft. You have in a 1 meter of wing structure, you have about 100 kilograms by the weight or the mass of the air contained inside a cube meter, and so 1 kilogram. And so in aircraft, this is about 110. If you consider an hydrofoil, okay, what happens? The mass of the structure with respect to the fluid mass is something like to the -1. Okay, so this number is very sensitive to the flow condition depending of air density and with respect to the structure of the fluid. Okay. Okay. So this is the table of our undimensional quantity. And sorry, this is green contour, not the blue, because the mass ratio is a parameter, it's not a state space variable. So we have a green contour here, just the other. And so we have the mass ratio, we have the frequency ratio. What is important? The problem are important. The mass ratio, the frequency ratio between the two involved, the two structural modes in the dynamic. Another important parameter is the elastic center location and the center body location. I take the time of the because we are delayed. Okay, so let me. I can stop.
Professore, si sente male. Un'altra volta, come prima.
And,
Sì, parla un po' l'audio.
Adesso si è tutto bloccato.
I can't see. Ok. Provo I try to go again, okay?
Ok.
Let me try. Ma il wifi io ce l'ho, forse mi sono ricollegato in questo momento. Ma... No, io c'ho la LAN. Can you hear me? Hello? Can you hear me?
Professore, la sentiamo a tratti.
I decided to interrupt this lesson. We will skip this lesson because it's not work in this condition, and I don't want you hate aeroelasticity for taking very careful on this point. So I prefer to work in another condition. I am very sorry for this. I apologize to you, and we will cover this in such way, and so we cannot work in this condition. Are you agreement or okay? I propose to interrupt. It's not possible to work in this condition. Okay, so I stop the recording. Can you hear me now?
È sempre male, prof.
Hello?
Sì, la sentiamo malissimo.
However, I want to. Okay, I stop this lecture here. At this point, we welcome